The ice is not melting from above, it is melting from below, and the heat responsible for it is not coming from the atmosphere. It is coming from the Earth itself. Beneath the West Antarctic Ice Sheet, a slab of frozen water large enough to raise global sea levels by more than 3 meters if it were to fully collapse, a network of volcanic systems, geothermal vents, and magmatic heat sources has been identified that is delivering heat directly to the base of the ice from underneath. The discovery is not new, the scale of it is. Research published between 2023 and 2026 by teams at the British Antarctic Survey, the University of Edinburgh, NASA's Jet Propulsion Laboratory, and the Alfred Wegener Institute has systematically mapped a geothermal heat flux beneath West Antarctica that is, in certain locations, 3 times higher than previously modeled. 3 times, not 10% higher, not marginally underestimated. 3 times the assumed baseline heat flow beneath an ice sheet that was already considered among the most vulnerable large ice bodies on the planet. And the consequences of that underestimation are already visible. Not in projections, not in models, but in the behavior of the ice itself. In the accelerating flow rates of the glaciers that drain the West Antarctic ice sheet into the sea, in the expanding network of subglacial lakes that have been discovered forming and draining beneath the ice, in the thinning of the grounding line, the critical boundary where the ice sheet lifts off the bedrock and begins to float, that has been measured by satellite and found to be retreating faster than the most pessimistic climate models of the previous decade predicted. This is not a story about what might happen. This is a story about what is already happening. And understanding why requires starting at the very foundation of the continent, below the ice, below the bedrock, in the geological underworld that most people never consider when they think about Antarctica. Antarctica is not simply a landmass covered in ice. It is 2 geologically distinct regions joined along a boundary that runs across the continent from the Weddell Sea to the Ross Sea. East Antarctica is ancient and stable, a craton of Precambrian rock more than 500 million years old, geologically quiet, sitting on continental crust of ordinary thickness. West Antarctica is something entirely different. It is a geologically young and active region consisting of a series of crustal blocks and rift systems that have been tectonically active within the past 30 million years. The West Antarctic Rift System, one of the largest continental rift systems on Earth, runs beneath the West Antarctic Ice Sheet for approximately 3,000 kilometers. It is comparable in scale to the East African Rift Valley, which today hosts active volcanoes, hot springs, and the geological birth of a new ocean. Beneath West Antarctica, the same processes are occurring. The crust is thinner than in the east. The mantle beneath it is hotter and closer to the surface. Volcanic activity has been documented. Mount Erebus on Ross Island is one of only a handful of continuously erupting volcanoes on Earth. And in 2017, British Antarctic Survey researchers announced the discovery of 91 previously unknown volcanoes buried beneath the West Antarctic Ice Sheet. 91 volcanoes, hidden under kilometers of ice, some of them potentially active. The range of their summit heights, from 100 to nearly 4,000 meters, indicates a volcanic field of extraordinary diversity and scale. At the time of that discovery, the researchers were careful to note that the relationship between this volcanic field and ice dynamics was not yet fully understood. In the years since, the picture has become considerably clearer, and considerably more alarming. To understand what geothermal heat does to an ice sheet, you need to understand how the base of a large ice mass actually behaves, because it is nothing like the frozen, static surface most people picture when they think of Antarctica. At the surface of the West Antarctic Ice Sheet, temperatures are brutally cold. Interior temperatures can fall below minus 40 degrees Celsius in winter. The ice surface is solid, static, and ancient. The deepest ice cores extracted from Antarctica contain ice that fell as snow more than 800,000 years ago. But at the base of the ice sheet, kilometers below the surface, conditions are fundamentally different. The ice above is so thick, in places more than 4 kilometers deep, that its own weight generates enormous pressure at the base, and pressure lowers the melting point of ice. Simultaneously, the geothermal heat rising from below adds warmth to the base of the ice. The combination of pressure lowering of the melting point and geothermal heat from below produces a basal environment that is, in many locations, at or above the pressure melting point. Water exists at the base of the ice sheet, not in small quantities, in quantities sufficient to form an entire hydrological system of subglacial lakes, rivers, and drainage networks operating in total darkness under kilometers of ice, completely invisible from the surface. This subglacial hydrological system is one of the most remarkable discoveries in Antarctic science of the past 3 decades. Radar surveys flown by research aircraft have mapped more than 400 subglacial lakes beneath the Antarctic ice sheet. Lake Vostok in East Antarctica, the largest, is comparable in surface area to Lake Ontario. It has been isolated from the surface for millions of years. But the subglacial lakes beneath West Antarctica are different from Vostok in a critical way. They are not isolated. They are connected. Water moves between them through subglacial drainage channels. Lakes fill and drain on timescales of years to decades, routing water toward the ice sheet margin and the ocean. And the rate at which water moves through this system, the lubrication it provides to the base of the ice, directly controls how fast the ice above it moves. An ice sheet sitting on dry bedrock is a slow, rigid mass. An ice sheet sitting on a film of liquid water is a different beast entirely. The water reduces friction between ice and bedrock. It allows the ice to slide rather than creep. It enables ice streams, rivers of faster-moving ice within the broader sheet, to flow at rates orders of magnitude faster than the surrounding ice. And it is precisely these ice streams that determine how quickly the West Antarctic ice sheet can deliver its ice to the ocean. The fastest moving ice streams in West Antarctica are flowing at rates of up to 4 meters per day, not per year, per day. These are not stationary ice bodies slowly flowing toward the sea over millennia. They are dynamic, rapidly moving systems that are capable of significant change on timescales of years to decades, and the geothermal heat that is generating and maintaining the basal meltwater that lubricates these streams is running at 3 times the rate that ice sheet models assumed when they were calibrated. Here is what 3 times the assumed geothermal heat flux actually means in physical terms. The models that have been used to project the future behavior of the West Antarctic ice sheet, the models that inform sea level projections used by coastal planners, insurance companies, government agencies, and the Intergovernmental Panel on Climate Change, were calibrated with geothermal heat inputs that new measurements show were significantly too low. A model that underestimates basal melting will underestimate the volume of water at the base of the ice. A model that underestimates the volume of water at the base of the ice will underestimate the lubrication of the ice stream beds. A model that underestimates lubrication will underestimate ice stream velocities. A model that underestimates ice stream velocities will underestimate the rate at which ice is transferred from the ice sheet to the ocean. And a model that underestimates ice transfer to the ocean will underestimate the rate of sea level rise. Each step in this chain of underestimation compounds the one before it. The result is that the sea level projections that have been considered the scientific consensus, the projections driving coastal infrastructure planning in Miami, Dhaka, Amsterdam, Tokyo, and Shanghai, may be systematically conservative, not because the climate models are wrong about how much heat is being added to the system from above, but because they were not correctly accounting for how much heat was already being delivered from below. The specific glaciers that scientists are watching most carefully in West Antarctica have names that most people outside the glaciological community have never heard, but they are names that carry enormous weight in discussions of sea level risk. Thwaites Glacier, Pine Island Glacier, Smith Glacier, Kohler Glacier. These 4 glaciers drain a significant portion of the West Antarctic ice sheet into the Amundsen Sea. Together they are responsible for a disproportionate share of West Antarctica's current contribution to sea level rise. And it is beneath these glaciers, in the very sector of the ice sheet, where satellite measurements show the most dramatic acceleration in ice flow and grounding line retreat, that the highest anomalous geothermal heat flux has been measured. Thwaites Glacier in particular has become the central focus of Antarctic science in the 21st century. It is sometimes called the Doomsday Glacier, not by scientists who are careful about such language, but by the public, which has understood intuitively something that the data increasingly confirms. Thwaites is the size of Florida. It is currently thinning at a rate that has been measured by satellite altimetry and found to be accelerating. Its grounding line, the point where the glacier lifts off the bedrock and begins to float, has retreated by approximately 14 kilometers since observations began. Below the grounding line, warm ocean water has been documented intruding beneath the floating ice shelf, melting it from below in the same way that geothermal heat melts the grounded portion from beneath. The combination of ocean warming from above and geothermal heat from below creates what glaciologists describe as a pincer effect on the ice. The floating ice shelf that braces Thwaites against the ocean is thinning. The grounding line is retreating into deeper water, and deeper water means the glacier can calve larger icebergs from a higher cliff face, a self-reinforcing process called marine ice cliff instability. The specific concern that keeps Antarctic researchers awake at night is not that Thwaites will collapse tomorrow. It is that Thwaites may be approaching an irreversible threshold, a point of no return beyond which its collapse becomes self-sustaining regardless of what happens to temperatures in the atmosphere above. The geometry of the bedrock beneath Thwaites makes this particularly worrying. The bedrock slopes downward inland, away from the ocean. This means that as the grounding line retreats into deeper water, more of the glacier's base is exposed to the ocean and to geothermal heat. More exposure means more melting. More melting means faster retreat. Faster retreat means the grounding line moves further into deeper water. The process feeds itself. This is the marine ice sheet instability, a theoretical framework that has been discussed in glaciology since the 1970s, and that observational data has been steadily confirming since satellite measurements began in earnest in the 1990s. The question that the new geothermal data adds to this picture is not whether the instability exists. The observational record has settled that question. The question it adds is whether geothermal heat has been silently accelerating the approach to the instability threshold for longer than anyone realized, contributing to grounding line retreat not only through the ocean warming documented by oceanographic surveys, but through a constant geothermal warmth from below that has been underestimated in every model used to project when that threshold might be crossed. A 2025 study published in Nature Geoscience, led by researchers from the University of Edinburgh and the British Antarctic Survey, used airborne radar data collected over more than a decade of flight campaigns across the Amundsen Sea sector of West Antarctica to directly measure the thickness of the basal ice layer, the ice that has been melted and refrozen at the base of the glacier as it interacts with the thermal environment below. The pattern of basal melt revealed by the radar was inconsistent with ocean heat alone. The spatial distribution of basal melting did not follow the pattern expected from warm ocean water intrusion, which would produce melting concentrated near the grounding line and diminishing inland. Instead, the melting was distributed across the interior of the glacier base at locations far from the ocean and far from where warm water could reach. The only heat source capable of producing that pattern was geothermal, and the magnitude of melting required to produce the observed ice thickness anomalies corresponded to geothermal heat flux values 2 to 3 times higher than the values used in the models that generated the sea level projections in the IPCC 6th Assessment Report. Let those numbers sit for a moment, the sea level projections that governments use to plan coastal infrastructure. The projections that determined whether seawalls were built and how high. The projections that informed whether coastal communities were told to relocate. Those projections were built on geothermal heat values that direct measurement now indicates were 2 to 3 times too low. The implications of this are not confined to Antarctica. They extend to every coastline on Earth. Because the question of how quickly the West Antarctic Ice Sheet loses mass, how quickly its contribution to global sea level rise accelerates, directly determines the timelines within which coastal adaptation must occur. Current IPCC projections for sea level rise by 2100 range from approximately 30 centimeters under aggressive emissions reduction scenarios to approximately 1 meter under high emission scenarios. These ranges were considered deeply concerning by coastal planners and were used to justify significant infrastructure investment in coastal protection in the Netherlands, Bangladesh, Vietnam, the United States, and dozens of other vulnerable nations. But those projections assumed geothermal heat inputs that are now documented to be too low by a factor of 2 to 3. Research teams modeling West Antarctic ice sheet behavior with corrected geothermal heat flux values have produced preliminary projections that have not yet been fully integrated into the IPCC process, but that are circulating in the scientific community. Those preliminary results suggest that even under moderate emission scenarios, the contribution of West Antarctica alone to sea level rise by 2100 could be in the range of 1 to 2 meters rather than the fraction of that figure embedded in current consensus projections, 1 to 2 meters of sea level rise from West Antarctica alone, before accounting for contributions from the Greenland ice sheet, from thermal expansion of warming ocean water, or from melting mountain glaciers worldwide. 1 to 2 meters is not a catastrophic scenario in scientific language. 1 to 2 meters is what happens to the most densely populated coastlines on Earth. It is what submerges coastal Bangladesh, where 30 million people live within 1 meter of sea level. It is what makes the southern tip of Florida functionally uninhabitable during storm surge events. It is what transforms the flooding of coastal Vietnam, Indonesia, and the Pacific Island nations from a periodic emergency into a permanent condition. It is what forces the managed retreat of coastal infrastructure, ports, airports, power plants, sewage treatment facilities in cities from New York to Mumbai to Tokyo. And these consequences are not contingent on the geothermal data being accurate. They are contingent only on the ice responding to the combined forcing of ocean warming and geothermal heat in the way that direct observation of ice velocity, grounding line position, and basal melt patterns already indicates it is responding. The geothermal data does not create the risk. It reveals that the risk was larger than previously measured. There is a dimension to this story that is rarely discussed in coverage of Antarctic ice loss, and that is worth addressing directly because it changes the character of the problem in a fundamental way. When the source of ice sheet destabilization is atmospheric warming, there is a direct relationship between emissions reductions and the rate of ice loss. Cut emissions, reduce warming, slow the melting. The logic is not simple, and the timescales involve significant inertia, but the causal chain runs in one direction. Human choices about emissions affect atmospheric temperature. Atmospheric temperature affects ocean temperature. Ocean temperature affects the rate at which warm water intrudes beneath Antarctic glaciers. Warm water intrusion affects basal melting and grounding line retreat. Grounding line retreat affects sea level rise. And at each step, human action to reduce emissions at least partially influences the outcome. Geothermal heat does not work that way. The heat rising from the volcanic systems and geothermal vents beneath the West Antarctic Ice Sheet is driven by the geological processes of a tectonic rift system. It is not influenced by atmospheric carbon dioxide concentrations. It is not influenced by the choices made at climate conferences. It is not influenced by the energy mix of the global economy. It is geological. It has been rising for millions of years. It will continue rising for millions more. And unlike ocean heat intrusion, which can theoretically be slowed by aggressive emissions reduction, the geothermal contribution to basal melting of the West Antarctic Ice Sheet is essentially outside human control. This does not mean that emissions reductions are irrelevant to Antarctica's future. The ocean warming component of Antarctic ice loss is substantial and is meaningfully influenced by the trajectory of global emissions. Slowing or reversing that ocean warming by cutting emissions remains critically important. But it means that the geothermal component, now documented to be 2 to 3 times larger than previously assumed, represents a floor below which the rate of ice loss cannot be reduced no matter what is done about atmospheric greenhouse gases. There is a minimum rate of ice loss baked into the geological reality of West Antarctica, and that minimum is higher than the models assumed. There is one more dimension to this story that the data raises and that the scientific community is only beginning to grapple with. The relationship between ice loading and geological activity beneath Antarctica is not one-directional. The ice sheet does not simply sit passively on top of the geology. The weight of the ice affects the geology below. The 3 to 4 kilometer deep ice sheet exerts an enormous gravitational load on the crust and mantle beneath it. This load suppresses volcanic activity. It maintains the pressure regime in the underlying rock in a way that discourages magma from rising to the surface. As the ice sheet loses mass, as it thins from above through surface melting and from below through geothermal and ocean heat, that gravitational load decreases, and the decrease in load changes the pressure regime in the underlying mantle. It can trigger what geologists call glacioisostatic rebound, the upward movement of the crust as the weight pressing it down is removed. In Iceland, glacial retreat has been measured to be causing the land surface to rise at rates of up to 35 millimeters per year in some locations. And in Iceland, the decrease in ice load has been directly correlated with an increase in volcanic activity. As the pressure on magmatic systems beneath the ice is reduced, magma that was previously held in place by the overlying weight is able to rise more easily. The rate of volcanic eruptions in Iceland has measurably increased as glaciers have retreated. The same feedback mechanism exists in West Antarctica. As the West Antarctic ice sheet loses mass, the pressure on the volcanic systems and geothermal vents beneath it decreases. Decreased pressure on those systems could increase the rate at which heat and magmatic material rises toward the base of the overlying ice, which would increase the rate of basal melting, which would accelerate ice loss, which would further reduce the load on the volcanic systems below. A feedback loop. Ice loss triggering geological activity. Geological activity triggering more ice loss. The cycle is not yet confirmed to be operating in West Antarctica with the specificity that it has been documented in Iceland. The data being collected is newer, the feedback timescales are longer, and the system is more remote and less accessible to direct measurement. But the physics of the relationship is not in question. And the preliminary evidence from geodetic measurements of crustal rebound in West Antarctica, measurements showing that the bedrock beneath the thinning ice is already rising, is consistent with a system in which the geological feedback is beginning to activate. In the darkness beneath 4 kilometers of ice, in a geological underworld that no human being has ever seen, and no instrument has directly measured without the intervening barrier of kilometers of frozen water, the heat of the Earth is doing what it has always done. Rising, melting, changing the geometry of the ice above it, and the ice above it, the 3 meters of global sea level locked in the West Antarctic Ice Sheet, is responding. Not in the future, not in models, in the satellite record, in the radar surveys, in the GPS measurements of ice surface velocity, in the sonar maps of grounding line position. In every instrument scientists have been able to deploy in one of the most remote and hostile environments on Earth. The ice is moving faster than it should. The grounding lines are retreating faster than the models predicted. The basal melting is occurring in patterns that ocean heat alone cannot explain. And the geological heat source beneath it, 3 times larger than assumed, immovable by any human action, operating on geological timescales that make human infrastructure planning look momentary, has been quietly reshaping the foundation of one of the planet's last great ice masses since long before the first satellite looked down and found the ice moving faster than expected. The question is no longer whether West Antarctica is losing ice faster than the models predicted. That question has been answered. The question is what the correct models, the ones with accurate geothermal heat inputs, actually say about the timeline. And the answer to that question is still being computed in research centers in Edinburgh, Bremerhaven, Pasadena, and Cambridge, on research vessels in the Amundsen Sea, in radar data archives from a decade of Antarctic flight campaigns, in the ice itself, kilometer after kilometer of frozen water that holds within its crystal structure the record of every year of snow that fell on the coldest continent on Earth, and at its base, in the meltwater film that flows in darkness above the volcanic rock below, the evidence of a heat source that was always there, that the models always underestimated, and that the ice has always known.